Okay, we have this example here, and again, just a beam with a couple concentrated loads on it. Again, you should have found that, like we said, the right-hand reaction is 7 kips, the left-hand reaction is 8 kips. There is no horizontal reaction over here at the pin because there are no horizontal loads. You have to get those reactions correct. If you don't get reactions correct on shear moment diagrams, then the rest of the problem is just wrong. All right? So, what do we say about the shear diagram? Well, it starts out at 0, and you're basically collecting loads. Okay? So the first load that you have right at this reaction is 8 kips, and it brings you up 8 kips positive. Nothing happens until you come over 2 feet and you hit that 5 kip load. A 5 kip load is going down, so what's it going to do to you? Bring you down 5 kips to the value of 3. Okay? Nothing else happens until you go another 4 feet, and at that point you have this 10 kip load, and it's going down. So you're going from a value of 3 to what? -7. Okay? And nothing happens over the last 4 feet until you hit that right-hand reaction, and that brings you back up to 0. Okay? So again, now this shear diagram is a little bit more descriptive than the first one we did. What does it tell us? Well, it tells us that the maximum value of shear is over here at the left-hand side, and it's 8 kips. And it also tells us if we're wondering where shear crosses through 0, okay, that occurs under the 10 kip load or at 6 feet out. Okay, any questions with that? Now again, if you wanted to do the moment at 1 foot or the moment at 2 feet, I mean, you can do that. You can step through it. A lot of times we're just interested in sort of the overall moment diagram. And in that case, all we're going to do is add up the areas of these geometric shapes. Calculate the areas separately and then begin to add them up. So, my first area is a rectangle, right? It's 8 kips high, it's 2 feet wide. I'll usually just write that product in here. Plus 16, it's plus because it's above 0. Okay, 8 times 2 is 16. The units would be foot kips. Okay? What's the area of the second sort of skinny rectangle here? Okay, 12. 3 kips high, 4 feet wide. It's above 0, so that's plus 12. What's the area of this bigger rectangle that's down below the 0, is in negative territory now? -7 high times 4, so that's negative 28. And again, the units here, or whatever units you have, these are kips and feet. All right? So, our moment diagram, we start out at 0. By the time we get 2 feet into it, what value are we at? Plus 16 foot kips. By the time I go another 4 feet, what's my value? 28, because I take that 12 and I add it to where I was at 16. Plus 28. I go from that point to the end of the beam, I add on negative 28 foot kips, and that brings me down to 0. So that's my moment diagram. What does that moment diagram tell you? What is the maximum bending moment on the beam? 28 foot kips, and where does that maximum moment occur at? 6 feet out from the left side. So you could take that information, 28 foot kips, maximum moment, 6 feet out, maximum shear of 8 kips, you could start to design the beam. You're going to need that information to design a beam. Yes?
So where it's, on the moment diagram, where it's 16 kips, is that point, is it 16.2? Like, what is it, the Y value for that?
The Y value is 16.
Oh, 16.
This value is
Oh,
16.
that's 16?
Yeah.
Okay.
16 foot kips. Just like the Y value here is just kips, the Y value here is, in this case, foot kips. Notice one thing that you'll start to notice, you might not have pointed this out the first time. Where's the maximum moment occurring? Where the shear diagram crosses zero. That's one of the things. These shear and moment diagrams always start at zero, end at zero, but the moment always takes on a maximum where that shear diagram crosses zero.
That'll be every time.
Every time. Now, in actuality, it could be a local maximum. As we get into more complicated shear and moment diagrams, you could actually find, depending upon the load and the beam configuration, you could actually see a diagram cross the beam several times. Okay, so only one would be the maximum, but you know, you get the idea. All right. How did we know that it was a straight line? I mean, we sort of knew from our first explanation that this is a straight line, but any idea how you can look at the shear diagram and know that these are all straight lines? Well, they're all straight lines because, I mean, they're different straight lines, okay? But they're all straight lines because you see the area, these are all relative to the area, right? How does the area change from one foot to the other foot in that first block? Is the first foot of area the same as the second foot of area? And the answer is yeah. How about down in this skinny little rectangle? How about the first foot of area in here? Is it the same as the next foot? Yeah. How about the first foot of area down here? Is it the same as the second? Same as the third? Yeah. So that means, you know, your moment in that area, in that block, is progressing, increasing, or decreasing at a uniform rate or a uniform pace. Okay? So that's why you know. That won't always be the case, but you know that now.